Welcome. Today we're going to look at two methods for solving the wave equation. That's this equation right here. It's a partial differential equation that governs wave. And so we're going to look at this via separation of variables first, and then we're going to solve the same problem using D'Alembert's method. So here is our solution animated. So if you're interested in that, stay tuned. On the left, I have a wave equation boundary value problem. U represents the vertical displacement of a string of length pi, which is placed on an interval from 0 to pi at position x and time t. Assuming proper units for length, times, and the constant k, and in our case, the constant k is c squared, the wave equation models displacement u subscript tt, and this is the second derivative of u with respect to time t, equals c squared. This is our wave speed, uxx, and this is the second derivative with respect to x of u. Partially. Using the method of separation of variables, solve the equation for u if the boundary conditions are u of 0t is u of pi t. Both of those are 0. And we also have ux 0 is 5 sine of 3x. And we also have u subscript t for the partial derivative of u with respect to t when t is 0. This is 0. Okay, so here is our boundary value problem summarized. So the method here is to let u, which is a function of both x and t, and up here I can see that it says u of x and y, but it should say u of x and t. So let's let this be equal to a function of x, phi of x, times another function of t, h of t. Now, this assumption right here is just a stab in the dark because it works for this particular kind of problem. So a wave equation in time and space, one variable of space. Okay, so what we want to do now is differentiate this partially a couple of times. So ut is the partial derivative with respect to t of this function of x and function of t. Now, since this function of x has no t's in it, that can float through that differential operator to the other side. And so we have this. Now, since this is only a function of t, we don't need to represent this derivative here as a partial derivative. We can just replace the derivative with just a dash. So we can call this phi of x times h dash of t for the first derivative of the function h with respect to t. Okay, and so this is u subscript t. You can see I'm using two notations for this. The subscript notation and the full partial derivative notation there. All right, so next we need to do this again so that we can substitute into this wave equation. So let's differentiate this again, but the same process will work. So utt is phi of x times h double dash of t. Okay, now let's do this for u differentiated with respect to x. So ux is the partial derivative with respect to x of phi of x times h of t. Now, h of t has no x's in it, so that can float through that differential operator. And we can express this as h of t phi dash of x. Okay, similarly, differentiating again with respect to x, we'll get uxx, and that is h of t phi double dash of x. Okay, and so now we want to take this line and this line, substitute these into our wave equation, and do some simplifying. Okay, so UTT equals c squared UXX. So let's take this and substitute in there for UTT, and so we get phi of x h double dash of t equals c squared. Now we substitute UXX, replacing that with this. So we have h of t phi double dash of x. Okay, so next we want to divide throughout by h. So we have h double dash of t over h of t, and we also want to divide by the c squared. So 1 on c squared. And so if we do this, we divide by phi of x. So you can see what I'm doing here. I'm putting the x's with the x's and the t's with the t's. Okay, so the reason to do this is so that we can solve this via the methods of separable differential equations. We have separated that there. Now notice on the left, we have a function of t. On the right, we have a function of x. This entire thing is a function of x. This entire thing is a function of t. So we have a function of t always equal to a function of x. So that can only happen when each of these functions are the same constant. So what we do is we call this minus a. That constant, we call it minus a. And the choice for calling it minus a, it's just because it makes things convenient later. Okay, so now this is two equations right here. So the first one, 1 on c squared h double dash of t over h of t equals minus a. And so let's call this equation 1. And then over here we have equation 2, which is this. So let's rewrite that. Okay, so two equations that have only the one variable in them. This one has an x in it. This one has a t in it. And of course, c squared, that's a constant. That's the wave speed squared. All right, so let's rearrange each of these equations. So rearranging this one, multiplying both sides by c squared h of t, we would get h double dash of t equals minus a c squared h of t. And then doing the same over here, we would get phi double dash of x equals minus a phi of x. Okay, so next what we want to do is take this over to the left-hand side and do the same with this one. So phi double dash of t plus a c squared h of t equals 0. And for this one, phi double dash of x plus a phi of x equals 0. So in other words, we have two second order homogeneous equations. This one's in t and this one is in x. So let's label this equation 3 and this one equation 4 that we got from equations 1 and 2. Now we know how to solve these homogeneous second order systems. We write down a characteristic equation. So for this one, the characteristic well, let's do it plural here. So we have, for this one, we have lambda squared plus a c squared equals 0. And for this one, let's just say different lambda, but I'll use lambda for it. Lambda squared plus a equals 0. So these are our characteristic equations that correspond to these second order linear homogeneous equations. Now, they are simultaneous equations, but these are different lambda. Okay, so let's solve this one. We've got lambda, taking this over to the other side. So lambda squared is minus ac squared. And so taking square roots, we've got lambda equals plus or minus c times the square root of minus a. Now, at this point, we don't know whether or not a is positive or negative. Okay, so we'll leave it as that for now. All right, now for this one, we've got lambda equals plus or minus the square root of minus a. And again, we don't know whether whether a is plus or minus. Okay, so at this point, we separate some cases. Case one would be something like, assume that minus a is positive, so a is negative. Okay, and so if we have assumed that, then that says that in the first case, this lambda equals plus or minus c root minus a. These are two real numbers. And so we can write down h of t is equal to some constant a1 e to the power of c root minus a times t plus b1 e to the minus c root minus a times t. Okay, but there's a slight problem with this because we'll see soon that it doesn't match the boundary conditions. And so I'll pull these up. So it won't match these, all right? However, we first need to see what happens in this case. Also, we would have phi of x equal to a2 e to the square root of minus a times x plus b2 e to the square root of minus a times x with a minus in front. Okay, so we would have this, and then because u is a product of phi and h, we would have this product of the two of these. b1 e to the minus c root minus a t, and then times a2 e to the square root of minus a x plus b2 e to the minus square root of minus a times x. So this would be u, but according to our initial values, let's see, which one do we want to use? Probably u of x comma 0, but u x comma 0 is 5 sine of 3x, and here u of x comma 0, as in here by this, if we're replacing the t with 0, we would have a1 plus b1 brackets a2 e to the square root minus ax plus b2 e to the minus square root of minus ax. Okay, now this is a contradiction because the square root of minus a is a real number, and so this is a real valued function. So there's no sine and cos there. So this is not equal to 5 sine of 3x. And so we have a contradiction in the assumption that a is negative. Okay, and so now let's look at the case when a is equal to 0. So case 2, assume a is equal to 0. Okay, so if a is equal to 0, then we have h double dash of t is 0, and b double dash of x is 0. And so integrating this with respect to t, we would get h dash of t is equal to a constant, say, c. And then integrating again, we get h of t equals ct plus another constant, say, d. Similarly for this, we would have b of x equals some constant, say j times x, plus another constant, say m. All right, and because u is a product of p of x and h of t, by our assumption, it's the product of these two linear functions, and this contradicts ux0 being a sine function. So we'd have djx plus dm for that, okay, which is not equal to 5 sine of 3x. Okay, so we see that a is not 0 in this case. Okay, so then we conclude we must have minus a being a negative number, or a being a positive, right? So equivalently a positive. Okay, which will give us solutions to each of these differential equations. It'll give us solutions that have sine and cos in them. Okay, so we must have a positive, and this means that what we have inside the square root here, in our case of h of t, that is a negative number inside the square root, and so we can express this lambda, different from this lambda. We can express it as plus or minus c root a times I, where I is the square root of minus 1. And similarly over here, this lambda, again, different lambda, plus or minus the square root of a times I. And so recall, in our solution to h double dash of t plus a c squared h of t equals 0, where we have our solution h of t equals a 3 cos of c root a times t plus b3 sine of c root a times t for that. Okay, now similarly for phi of x, we get phi of x equal to a4 cos of root a times x plus b4 sine of root a times x. Okay, now what we want to do is use our boundary values. So let's use u of 0t equals u of pi t, both of these equal to 0. Okay, and so what we're going to do here is we're going to replace the x values with 0, and then after we do that, we're going to replace the x values with pi. Okay, so let's go ahead and do this. So we have u is the product of these two, so u 0t equals, now rather than writing this all out again, I'm just going to put h of t, but for this, replacing x with 0, we would have cos 0. Now cos 0 is 1, so we have a4 for that, and here sine of 0 is 0, so we have plus 0. We just have this. So this is equal to 0. All right, now u of pi, comma t, is h of t. Now we're replacing the x with pi, so cos of pi root a, so let's just put phi of pi for that. This is equal to 0. All right, and so for this to be the case, because h of t is not 0, and what else do we know? Well, from this one, we get phi of pi equals 0, and we get a4 has to be equal to 0. All right, and so let's now consider u x0 is 5 sine of 3x. And so what this is, we are then in here, we're replacing the t with 0. So we have ux comma 0 equals a3 cos of 0, that's 1. So we just have a3. Now sine of 0 is 0. So we have a3 phi of x is equal to 5 sine of 3x. And so this gives us, we get phi of x equal to 5 over a3 sine of 3x. Now this agrees with phi of pi equal to 0, because if we put pi in here, we've got sine of 3 pi. That is a multiple, or an integer multiple of pi, and so sine of 3 pi is 0. So it agrees with phi of pi is 0, and a4 is 0. Okay, remember a4 appears here in the expression. All right, so now that we have this, let's differentiate our phi of x so that we can get a little bit more information about the letter lowercase a. Okay, so I'm going to rewrite phi of x is equal to 5 over a3 sine of 3x. And then we're going to differentiate this. So we have phi dash of x is, now we need to use the chain rule for this. This is a constant, but we need to use the chain rule here. And so what that will do, we will have a multiplicand that is the derivative of 3x with respect to x, and that derivative is 3. So 3 times 5 is 15. So we have 15 over a3 cos of 3x for our first derivative. Okay, now differentiating this again with respect to x. Again, we use the chain rule. Now the derivative of cos is minus sine. So we have minus 3 times 15 is 45. So minus 45 over a3 sine of 3x. Okay, now phi double dash of x plus a, phi of x is meant to be 0. So substituting these two in here, or sorry, this and this in here, we have minus 45 over a3 sine of 3x plus a times 5 over a3 sine of 3x is 0. Okay, so factorizing out the a3, what we get is 5 lowercase a minus 45 all over a3 times sine of 3x. This is always 0. So that means then that that numerator in there has to be the one that is 0. So 5a minus 45 is 0. And we get a equal to 9. 9 times 5 is 45. So we've worked out that lowercase a has to be 9. Yes, that's positive. Okay, and the square root of 9 is 3. Okay, so coming back to h of t is a3 cos of 3ct, because we now know the square root of a is 3, plus b3 sine of 3ct. And so u of x and t is the product of phi of x and h of t, which is 5 over a3 sine of 3x, and then times this. Okay, fortunately almost finished with this one. So next, what we need to do is take the derivative of this line with respect to t so that we can use our last boundary value, u subscript t, x 0 is 0. Okay, so to use this, we need to differentiate this line with respect to t, partially. So u subscript t of x and t is, now since this piece of it only has x's in it, we just differentiate this part. And why don't we just put this a3 in, because I think that makes it easier. So we have 5 sine of 3x times the partial derivative with respect to t of, now a3 over a3 is 1, so we just have cos of 3ct plus b3 over a3 sine of 3ct. All right, so we need to differentiate this with respect to t. So the derivative of cos is minus sine, but we need to use the chain rule, and a 3c comes out. So we have minus 3c sine of 3ct for the derivative of cos of 3ct with respect to t. And then for this, the 3c comes out via the chain rule, and we have plus 3c b3 over a3 cos of 3ct. And so this is u subscript t of x and t. All right, so we want to use this boundary value. So now in this identity, we need to replace the t, according to this, with 0. So remember, sine of 0 is 0 and cos of 0 is 1. So here we have 0 for this. When we sub in t is 0, and over here we have plus 3c b3 over a3. Okay, and so this is meant to be equal to 0. And so what this tells us then is 15 for 3 times 5, c b3 over a3 sine of 3x is 0. But it's not sine of 3x that's 0. It's this that's 0. We know that the wave speed shouldn't be 0, so it has to be b3 that is 0. So we must have b3 equal to 0. So then what we get, having a look at this, we have h of t is a3 cos of 3ct, and we already have phi of x is 5 over a3 sine of 3x. So taking the product of these two, we get u of x and t equal to the product of these, but you can see in the product the a3 will cancel, so we have 5 sine of 3x cos of 3ct. Okay, so we have solved that wave equation boundary value problem. And next we'll do the same problem but using D'Alembert's method. So I'm not going to say easy peasy for that one, because that pretty much took a half an hour to go through question 10 via separation of variables, but I will say easy peasy about the next one, because there's a formula for this. So in question 11, we're going to solve using D'Alembert's method. And so that just gives us a formula for the solution to the wave equation, and it's 1/2 h of x minus ct plus h of x plus ct bracket plus 1 over 2c integral x minus ct x plus ct. So this is a definite integral of k of s ds, where h of x is u of x of 0, and in our case 5 sine of 3x. So in other words, this is not the same h of x as we had in the previous question, which was actually h of t. And k of x is u subscript t x 0, which in our case is 0. All right, so let's get on with it. We'll do this. So in our case, u of x and t is 1/2 5, because h of x is 5 sine 3x. So we have 5 sine of, in brackets, 3. Now what we're doing is we're replacing the x with x minus ct. The 3 bracket x minus ct plus 5 sine of 3 times x plus ct. Okay, I need to end this bracket, matching there. And then we have plus 1 on 2c times the definite integral x minus ct x plus ct of k of s. Now k of s in this case is just 0 because u subscript t is just 0. All right, and so that integral is the integral of a constant, right? And so we're just going to get 0 for this piece. So we can pull the 5 out of this and say this is 5 over 2 sine of 3x minus 3ct plus sine of 3x plus 3ct. Now, fortunately, we can use our angle addition formula for this. So just note, angle addition formulas for sine and cos. So we have 5 over 2 sine of 3x cos of 3ct minus sine of 3ct cos of 3x plus sine of 3x cos of 3ct plus sine of 3ct cos of 3x. Okay, now what do you notice here? We've got some vanishing with these two. And these are identical, so we actually have 2 of those. So we end up with twice sine 3x cos 3ct here, but 2 over 2 is 1. So we end up with 5 sine of 3x cos of 3ct. And this matches what we got using separation of variables. But this is the very simple D'Alembert's method. So here is our solution animated. Easy peasy.